Welcome learners. In today's lecture, we are going to continue our discussion on charge distribution. In the previous lecture, we talked about volume charge distribution, and now our charge distribution will be on line charge density, or how the charges are distributed over a straight line. We have already seen the point charge and volume continuous charge distribution. So let us consider the line charge distribution. So this is the preamble before we go into the details of the topic. In this scenario, we will see how the charges are being distributed on a thin line, or what we called as a filament. So analysis will be on a piece of wire having very thin cylindrical form or a very small radius, and the idea will be how the charge are distributed. For example, you can see that if we have the rectangular coordinate systems, this is our z-axis, this is our y-axis, and our x-axis is coming out of the screen. So we assume a very thin line shown here in the color green that has a very small radius, although it's a cylindrical wire. So since it's a cylindrical wire, our analysis will be in the cylindrical coordinate systems for this charge distribution, and we will keep the axis to be a z-axis as the wire is placed along the positive and negative z-axis. And then we are going to understand what happens when the charges are uniformly distributed on this thin filament or piece of wire, and how it is going to affect a test charge which is placed, let's say, at point P. So what is the effect of any of one of the charges placed anywhere along this green line or thin wire, and how it is going to give us the required electric field. So this is the analysis that we want to do. So let us begin understanding the charge distribution on a line. Charge distribution on a line. So we have two forms of distribution that we normally deal with when working with distribution or field of line charges. The first is if we have a finite charge distribution, and the second can be an infinite charge distribution. Again, the distribution has to be on a wire or a piece of thin wire. So when we talk about the charge distribution, or especially line charge distribution, we'll keep in mind that our charge density will be represented by rho and L. So this is the symbol of line charge density. Previously, for volume charge density, our symbol was rho V, but for line charge density, this is going to be rho L. So this is the symbol that we are going to use. So now what is a finite charge distribution? So for the finite charge distribution, let us consider a circle, and it has a center and a radius. So this is the origin and this is the radius, and it is making any certain angle theta, and the charges are uniformly distributed, or finite number of charges are distributed on this circle of radius r. So in order to do the analysis on this circle, we need to consider a portion that is forming a line. Let us say I want to focus on this point. So this is one portion where I can consider one part of the circle to have a line structure, or I'm selecting a very small region. Since I'm selecting a very small region, so the angle through this region is going to be d of theta. And since the charge selected is of a small quantity, so it's going to be a differential charge d of q. So we can define rho L, which is the line charge distribution, as rho L is equal to the small quantity of charge per unit length. In this case, it is going to be d of L. So let me write this symbol correctly. So this is line charge distribution, rho of L, and its unit is going to be coulomb per meter. So if I want to further define what is this d of L, so this is combination of the radius covered from the origin to the theta, or the small angle that we got, that is d theta. So this is how we mathematically define a finite charge distribution on this circle with radius r and angle theta. But our topic of discussion is infinite charges. So finite charges is also shown to you in terms of the mathematical expression, because most of the problems at the end of this second chapter deal with these forms of questions, and we are going to tackle one of the examples associated with the circular distribution of charges. But now let's focus to the infinite charge distribution, or for a small thin wire. So let us say I have a small thin wire along the z-axis. In order to understand better, we just increase it a little bit in terms of its thickness, and this is all covered wire. So it is on the z-axis from plus infinity to minus infinity, and it can go on like this. And we have charges or infinite charges on this infinite length of wire situated along the z-axis. So when we are going to do the analysis, we are going to again select a small portion of the charge. So in this example, or in this scenario, their charge will be d of q, and we know that the length of this line where the small portion is selected is going to be d of L, which is going to be the same differential charge d of q. So the equation for the line charge density in this scenario will remain the same, that it is the ratio of the length per unit, it's the ratio of the charge per unit length. So this is the line charge distribution for this scenario as well, and this is going to be our reference ground. Okay, so this is the infinite large line charge distribution that we want to do our analysis on, and we need to find what is the mathematical expression for the electric field when we have this form of infinite line charge distribution. So before we proceed on finding the equation for the electric field, there are 2 points that we have to keep in mind, or 2 very important points when dealing with line charge distribution. And that is basically going to help us understand in which plane symmetry our charges are lying, and which components of the electric field is present over there. So what are those 2 points? So those 2 points are associated with finding the direction of the electric field, of the E field, and how it varies. So how the E field changes. So the points are, the first point is, when working with the coordinates, we need to know which coordinates that can be x, y, z, rho, phi, theta, or r, theta, phi. So with which coordinates the field doesn't change. Which field? The E field does not change. And secondly, we need to know, once we have figured out the first point, that which components of the field, which components of the field or the E field are not present. So this will give us an idea visually that where the electric field is existing and which planes we need to work it. So in order to understand these 2 points, let us take a scenario where we have the line charge distribution. So let us draw the axis. So we have x-axis over here, z-axis, and let us say this is our y-axis. Now, since our analysis is on an infinite line charge located along the z-axis, so let us say this is the line charge, or line that is filled with infinite charges. So it is from positive infinity to negative infinity. So let me populate this with the uniformly distributed charges, and it is going on like this to positive and negative infinity. So now what is going to happen? We select any point, let's say point P, along the y-axis, and we select a portion of a charge. So this portion of a charge is basically going to be our d of q. So let me use another color to differentiate better. So this is the smaller portion of charge which we have selected from the infinite charges, which we are calling as d of q, and we want to see the effect this charge has on this point P. Obviously a certain force is applied from charge to point P, and the result is the differential electric field as the force is applied on that charge which is placed at point P. Let us populate it with the remaining elements. So let us say from the origin to the point P, the horizontal distance or the position vector is r. From the charge we have selected along the z-axis, and the distance from that point to point P is r dash, or we can also represent it as rho, because this is cylindrical coordinate system, so we need to define the axis according to the shape of the line which is cylindrical. So this is rho l, and then we also want to know what is the azimuthal axis. So we move from x to y, so this is our phi, and there is a certain angle being made over here. Let's call this theta. What is this theta angle about? We'll come to it shortly. So this is the position that I am getting. The position vector can also be r dash for this case. Okay, so now, sorry about that. So the position vector from origin to z-axis where the charge is lying, let me call this as r dash. So these are the points that we have, and now we want to see how the 2 points are being applied. So let us take this image and apply it on the point. So we have designed the line charge and placed it on the relevant axis, which is the z-axis. We have defined the rho, phi and z-axis for the cylindrical coordinate system. Now, how to justify these 2 points? So let us say we want to find that with which electric field or with which coordinates the electric field does not vary or does not change. So if you remember that there are certain symmetries associated with fields, those asymmetries are that if we are talking about the cylindrical coordinate system, we have, whenever we move the rho, we say this is a radial symmetry, or if the object is moving around or along the rho, if the object is moving along the azimuthal axis, we say this is azimuthal symmetry, and if we are moving along the z-axis, we say it is the axial symmetry. So in all of these 3 symmetries, we want to see which symmetry is not affecting the electric field. So let us do 3 scenarios to validate the first point, which is over here. So let us say in this whole scenario, the first point we take is that we vary phi, or we move the object around the phi while keeping rho and z value constant. So in second scenario, we are going to keep, or we are going to vary z, and we are going to keep rho and phi at a constant value. And then for the third part, we are going to vary rho while keeping phi and z constant, and we are going to see that for all these 3, which is going to affect the electric field distribution created. So let us say for the first scenario, we want to keep a constant point for rho and z, and we want to move with phi. This means, let us say we want to take a constant point over here. So this is my point A. So the value of rho is along a certain value, let's say it's a constant, and the value of z is 0 for in this case, and we are just moving along the phi, which is over here. So whatever the electric field we found at A is not going to change because the object will be moving. So let's say if this was the point and the object is to be moved, so it is going to move only around phi from 0 to 2 pi. This means the object is going to just rotate along its own axis like this. So it will just be moving in a circular direction, and its value of electric field will also move along it. So it is not going to affect the value of the electric field. This means for the first case, E field is not going to vary. It is not going to change because it will just be moving in a circular or it will be rotating around its axis. By axis I mean its center point. So it is not going to be affected when we vary the phi. Now let's go to the second point, and we want to see what is going to happen if we move the object in the z-axis. So if we move the object in the z-axis by keeping rho and phi constant, let us say if I take the value of rho to be some point again over here, so this is my rho, and the value of phi is also over here, so it is the same point over here. And now what I'm going to do is I'm going to move up and down in the z-axis, so it will either go up or it will go down. But again, the electric field is not going to vary because the radial point and the phi is a constant value. So this means that the electric field again is not going to vary for this scenario, because we are just moving the point in space either to the plus infinity top position or we are moving it to the bottom position. Nothing is going to happen. Now let's come to the third point and see what is going to happen if we vary radially and keeping phi and z constant. So now this is a point, and you might have already guessed, this is going to vary the value of electric field. Why? Because this is the radial movement. So if my point is at here, the electric field is different. If I move backward radially, so the electric field will be different. So this means that moving in the radial position back and forth is going to affect my electric field. So radial movement is causing this change. So this is how we interpret the first point, that with which coordinates the electric field varies. And second point can be assumed from the first, that which components of the field are not present. So obviously, since electric field is varying around rho, this means that E of rho vector will be available and the remaining components will not be available. That is going to be d of z and d of x. So how we can interpret that as well? So for the second point, let us go back to the same image. Let's say we do it over here as it is more clear. So we know that the electric field formed is in this direction, following the radial line. So the two components of an electric field will be, one component will be along the horizontal axis, which we are calling as dEy, and other will be along the vertical axis, which we are calling as dE of x. Now you can see in terms of symmetry, sorry, this is dE of z, because this is along the z-axis. So in terms of symmetry, you can already see that dE value is not going to change because it is along the radial point. If we consider this r equal to rho, because this is also the radius, so the point that is going to be cancelled out is going to be dE of z. Why? So let us say now if I select another charge d of q but along the negative z-axis. So if this charge is selected, we want to see its effect on this point, which means that the electric field now will be in this direction. And if we make again two components of the electric field, so one will be again along dEy, which is going to be the same as they are overlapping, but the other will be in the dEz. So since this is a symmetric structure, these dEz and dEz components will be cancelled out, and hence the only component that is going to be available will be along dEy, which we can term as dE rho, because the radial element is equal to the rho element, which we can see from here that this rho, which is moving in the radial direction, is similar to this r, which is the position vector from point O to point P. So this is how we figure out which components are available and with which coordinate system the electric field is not varying. So keeping in mind that we talk about the z-axis, it means we are moving in the top to bottom position, which is known as axial symmetry. If we are moving in a 360-degree rotating, so it is the azimuthal, and if we are moving front and back, this is the radial symmetry, and in our scenario radial symmetry is affecting our analysis. So this was a description of the 2 points. Now let us come to the second point of the discussion, and that is to prove the electric field equation for the line charge distribution. So in order to prove the electric field equation for the line charge distribution, let us again draw the axis of interest and populate it with the correct values. So again, I'll draw the rectangular coordinate systems. So this is Z, this is Y, this is X. Our line or infinite charge line is lying on the Z axis, that is from the positive to negative infinity along the Z, and the charges are distributed uniformly. We select one of the charge from this line and we call it as d of q, and we want to see the effect it has on a point, let's call this P. So the combination of these lines is represented by a symbol which is known as line charge density rho of L, and we want to see the effect this charge has on this point P, which in turn is translated as the differential electric field because we are selecting a small charge of dq. Now, what is the value of dq? Obviously, dq is lying along a line, so we can say that this line is d of L and this is equal to the coordinate where it is lying, so it is d of z. Next, we want to define the correct coordinate systems because the wire is cylindrical in nature. So we know that this is the origin, and if we move toward this point, this is position vector r. If we move from this point, this is the radial value rho. The angle from this point to here is phi. There is one angle mean made over here called theta, which is not part of the cylindrical coordinate system, but it has importance over here, which we are going to discuss. If I take point from 0 to z axis, then this distance vector is r dash, and components of the vector of dE is along dEy as we saw previously, and the cancelling vector is dEz. This cancels if we select another charge from the negative axis and take a point over here and go over here for dE. So the charge for this component is going to be dEz, which is going to cancel out from this, and dEy remains the same for both of the axes. So this is again the population of the elements that we saw. New additions to this will be that what is the axis at point P where we want the effect to know, and what is the axis of the source charge. So it is going to be at 0, 0 and z axis, and point P is located, let us say point P is located at 0, y and 0. So these are the coordinate systems. Why we need this? Because it is going to help us solve the equation. So we have prepared our scenario with certain pointers that our line charge is lying on the z-axis from positive to negative infinity. We are using the cylindrical coordinate systems for the analysis, and the charges are lying along the line d of L, which is equal to d of z, and we have selected a small charge that is d of q, and now we want to find the electric field or the differential electric field to start our analysis towards the final or total electric field, which is going to be E. So our point and axis are decided, and we know that our point or the source point, let's put it like this, source point is along 0, 0 and z, and the focal point or the charge or the test charge is lying along 0, y, 0. This is basically your point P, where we want to find the electric field effect. The component that is available is only going to be, or the components, let's put by the definition, is dEz and dEy, which are not present in the analysis. So the only component present is along the y-axis. Okay, so the dE component is going to cancel out, and the only component that is present is going to be dEy. So now let's find the equation for the electric field intensity for the scenario which we have just created. So we know that the differential electric field for any charge or a point charge, let's say, comes out to be d of q divided by 4 pi epsilon naught into absolute of r square with the unit vector a of r. So this is our basic equation, and we know what is the value of d of q. So d of q, which is the incremental charge, is going to be the line charge density multiplied by d of L, and we also know that d of L in this case is along the z-axis, so it is going to be d of z. So this is the value of the differential charge. Input this value in the equation of the differential electric field. So our equation for differential electric field updates to rho of L into d of z divided by 4 pi epsilon naught into r absolute square into a of r. Now we need to figure out what is r. R is the distance vector which is from the source, our point here, to the point with the test charges, that is point P. So r is the distance vector which is basically the difference of the position at point P minus the source which is at z-axis. So I can write it as, it is going to be r dash minus r, or it's going to be, or we can just write it as r minus r dash, because the unit vector is r and for z-axis it is r dash. So it comes out to be 0 r 0 minus 0 0 z. So these are the axes. Here this y is along the radial path r, that's why I have written r. So it comes out to be r of along ay minus z of unit vector a of z. So this is the value of r, and if we take the absolute of this, so it becomes square of the scalar components under root. So this is the value, which means our unit vector here, a of r, it comes out to be r divided by absolute of r, which is r along ay minus z along az divided by under root r square plus z square. So this is the value of the unit vector which we have found. So now let's put everything into the equation. Let's call this equation 1. So our differential element then becomes rho of L multiplied with d of z divided by 4 pi epsilon naught. So the value of r, and since this is an absolute square, so it is going to be r square plus z square, and then the unit vector comes out to be r a of y along, and then z a of z divided by r, which is r square plus z square. We can further simplify the equation as rho of L d of z divided by 4 pi epsilon naught. So I can combine these two values as 1 by 2 plus 1, so it becomes r square plus z square at the power of 3 by 2. So this is what I am getting, and the unit vector now comes out to be r a of y, and that is the answer for the differential element for the time being, which means the effect the electric field is producing from a single charge. Now where does this value disappear to? So this has become 0, because if we take the charge on the minus z-axis and we take the charge from the positive z-axis, so we just saw that the component along the z-axis cancel each other out. That's why the unit vector along z-axis is not included in equation number 2 for the differential electric field. So this is what we are getting as the differential part, but we want to know what is the effect or overall electric field effect of these charges at point P. So in order to find the overall electric field, we take the integral of the equation number 2. So equation number 2 is, so let me write equation number 2 again. This is the differential element of rho of L d of z divided by 4 pi epsilon naught. This is r square plus z square with the power of 3 by 2, and the unit vector is r a of y. Now in order to find the total electric field, we are going to integrate this. So this becomes integral of, the limits will be from minus infinity to plus infinity, and these limits are for the z-axis. The equation becomes rho of L, and this is going to be, so let me bring r inside the equation. It becomes d of z 4 pi epsilon naught r square z square 3 by 2, and this is along the a unit vector a of y. Okay, so how can we find the integral? So first let's deal with this uh, integral limits over here. So in order to deal with this, let's first change the limits. So let's change the integral limits. So we want to change the integral limits. Why we want to change it? Because if we go back to our original image, we can see, let me take a clear image. Okay, so we want to change the limits from minus infinity to infinity because our elevation angle is from, so if this is my axis, this is y, this is x, and this is z. So our movement along the z axis, we don't want to go from minus infinity to infinity, rather we want to go from 0 to 90 and then to 180. So this becomes that I want to move from 0 to pi by 2 to pi. So I want to change the negative and positive infinity to these limits. So in order to do so, I'm changing the limits. So how can we do that? So if we look back at our analysis, I mentioned that we introduced a theta over here. So this portion, this image or this triangle is going to help us change the limits. If we focus on this triangle, so I'm just zooming in on that triangle. So this was the theta, this was our point P, this is our origin, and this is the distance vector r, and this is the z-axis. So again, I've just taken this green highlighted angle or the triangular or 90-degree angle to be precise. So I know this is distance is r and vertical axis is along z-axis. So trigonometric identity tells me that I can apply the tangent theta identity over here, where tangent theta is going to be r by z. So this is opposite to adjacent, if you remember those identities. So if I have opposite, so this is my hypotenuse, this is my opposite to hypotenuse, and this is the adjacent, or sometimes we call the adjacent as a base. So this is the ratio. Now to get the value for z, I am going to transform this into cot theta to make my analysis easy. So this becomes z by r. So z is equal to r cot of theta, and let's differentiate it with the terms to theta. So it comes out to be minus r cosecant square theta, and let's shift the d theta from here to the other side. So this is the equation I get for z and d of z, which is going to be helpful for analysis when find the integration. Now from this equation, let's find the value of theta. It comes out to be cot inverse z by r. We put the value of z as plus infinity and minus infinity. Hence, when we put the value of plus infinity and minus infinity, the angle comes out to be, for negative infinity and positive infinity gives me a value of 0 and negative infinity gives me a value of pi, and hence we have changed the limits from positive and negative to 0 and pi. Thus, our updated equation now becomes, or let me, so our E total or the integration that we want to do has now limits from pi to 0, and then our value comes out to be, so now I'm going to integrate everything into this equation. So rho of L remains the same, R will remain the same, d of z, I'm going to have this value, which is minus r cosecant square theta. So, and then this is along ay. Let us keep 1r because they will get multiplied. So it is going to be r square, and this row becomes negative. Then I have 4 pi epsilon. Here r square will be as such, and value of z is to be incorporated. That is going to be r square cot square theta, and then we have that's it, d theta. So this is r square and cot square theta, and I think I missed d theta for this side when I incorporated the value of d of z. So d theta is also into this. So this is now the equation when I have input everything. Now I can take r square as a common from here. So my equation can look like pi to 0 minus rho of L r square cosecant square theta d theta divided by 4 pi epsilon naught. If I take r square common, then okay, I missed 3 pi 2 over here. So then this becomes 3 by 2, and this will become 1 plus cot square theta with the power of 3 by 2, and ay will go along the way. So this and this cancels out. I'm left with r cube, and then r square can be cancelled with 1 of the r cube. So then my equation further moves to get simplified as minus rho of L. This becomes cosecant square theta d theta divided by 4 pi epsilon naught. So here I'm left with r, and this 1 plus cot square theta, this becomes as an identity of cosecant square theta. So I can write it as cosecant square theta with the power of 3 by 2. And if I solve this or bring it out from the brackets, so the square and the square cancels out, and this cosecant square is going to be cancelled out with this cube. So my equation now looks something like pi to 0 minus rho of L. On the top side we have just d theta left now, divided by 4 pi epsilon naught, and I have r, and this becomes cosecant theta along ay. So this is what I am getting. So now my 1 by cosecant theta, I can simplify this portion. So this comes out to be sine of theta. So let me utilize this space. So now the range becomes pi to 0 minus rho of L divided by 4 pi epsilon naught into r, and 1 by cosecant becomes sine theta d theta along ay. Now I can integrate this limit with this sine theta and d theta. So my answer comes out to be minus rho of L divided by 4 pi epsilon naught into r, and this is pi to 0 sine theta d theta along a of y. Then I can simplify it. So now electric field comes out to be minus rho of L divided by 4 pi epsilon naught, and if you integrate sine theta, it comes out to be minus cos theta. You input the values, so you get minus cos theta with limits from pi to 0 along ay, and once you input the limits into cos theta, you should get the answer of, after simplification, as rho of L divided by 2 pi epsilon naught r into a of y. So this is the electric field of a line of charges, and in the book we can simplify it further, as we can write it as rho of L divided by 2 pi epsilon naught. This r can be replaced with rho with an absolute sign, and this ay is now going to be along the a row vector. And why we can do this? This equation is also acceptable for the electric field in the units of volts per meter. Why we can do this? Because we know that this row which is coming along this line is the same radial distance which is going from origin to point P, represented by r. So r can be replaced by the value of rho, which is the radial component of the cylindrical coordinate system, and hence we can have this equation as well. So both of these equations are acceptable. And how we do this? Because r becomes rho, and obviously ar will become a of rho. So this is the condition that we have utilized, and hence we have proven the equation for the electric field of line of charges. Another point to remember whenever we are dealing with line charge is that, so we can say a note is that whenever, or if the line charges are placed along z axis, they can be placed along y axis, they can be placed along x axis. For all these scenarios, remember that if it is placed along these axes, then their respective coordinates will vanish, which means if it is placed along z axis, then dE of z will become 0, because they will cancel each out as per symmetry. For the y-axis, dy will become equal to 0, and for the x-axis, d of ex will become equal to 0 because of the symmetry in the positive and negative axis. What do we mean by symmetry? This is what we mean. If the line is placed along the z-axis, then dEz and dez for positive and negative side will finish, or it will vanish. If it is along y-axis, then dey will cancel out. If it is along x-axis, then dex component will vanish out. So this was the proof for the electric field intensity of line of charges, and the important elements were the 2 points which we saw over here. So these points are always to be respected whenever solving the problems associated with line charges. So now let's talk about what happens if we offset the line. Rather than we have the line on the center which is along the origin, we offset it. So now what happens if we do something like this? We want to find the electric field for off-axis line charge. So this is a scenario that can happen. What does it mean? Let's first understand it visually. So the idea is that the line charge is located not on the axis. Line charge is now located parallel to the axis. So parallel to the axis. What does it mean? For example, let's say our points are 6, 8 and 0, but in this case we keep it z because we are along the line's location which is on the x-axis. So let us say if this is my coordinates y, x and z, and now my line is not located on the origin, not on the z-axis, no, it is located at this point. So if I locate at this point, this comes out to be x is equal to 6, y equals to 8. So this is something like, so my line is now located along this point. So this is the point where my line is located. Let's say now point is 6, 8 and z axis. So this means that now my line is off axis and the charges are distributed uniformly along this infinite line. And I want to now know the effect of any of the charge, let's say on the point over here at point A. So it can be any point along the x, y and z. So this can be the scenario where the line charges are off axis, not at the origin, or it is now parallel to the z axis. So whenever this kind of a situation happens, what is going to be the equation for the electric field? So another point to remember is whenever we are dealing with point charges, we move from the charge, let's say any charge. So always the field line, which is the energy coming from the charge to the point where the test charge is. Let's say in this case, we want to move from this dq charge to this point A where the test charge is. So always draw a perpendicular line towards the point. So wherever the line charge is, you have to draw the perpendicular line. Keep this point in mind. In the coming examples, it will be clear. But as a starter, we always want to make a 90-degree angle with the line of charges, and that line is going to be our radial line. If we are talking about the cylindrical coordinate system, this becomes rho, and its unit vector is going to be a of rho. So always make a 90-degree perpendicular line from the line of charges wherever it is located. Now if this is the scenario, you want to find what is the electric field in this case. So we know that the electric field of a line charge is rho of L divided by 2 pi epsilon naught absolute of rho multiplied by the unit vector a of rho. So in this case, let us see what is the value of rho, which is basically the distance vector from the source to the point. So rho in this case comes out to be, since we have a point x, y and z, so we can write it as x minus 6 a of x, then plus y minus 8 a of y. And another point that you now need to know is that the z axis will always cancel each other out, and this is the representation of letting us know that our line is lying on the z axis. Whatever the value of z axis is, we have to select coordinate points for the test charge and the source, whichever is given, such that the difference comes out to be 0. That's why our position vector is not going to have the component of z axis, and we have already seen the 2 points at which component is not available. This is one of the representation of that. So this is the rho vector, and now if I want to find the absolute of this rho vector, so again I'm going to just square the scalar quantity. So in this case, it is going to be x minus 6 whole square plus y minus 8 whole square. So this means now my electric field equation with all the parameters comes out to be rho of L divided by 2 pi epsilon naught. Now input the value of rho of P, that comes out to be x minus 6 square plus y minus 8 square, and the unit vector in this case is going to be, so I'm going to write the unit vector over here, a of r. So if you don't remember, unit vector in this case is going to be the value of rho divided by the absolute of rho, where the rho is our distance vector as such. So incorporate this over here, so it comes out to be x minus 6 a of x plus y minus 8 of y divided by the same value, which is going to be under root x minus 6 whole square plus y minus 8 whole square, and this is the same value as we have over here for the under root. If you want, you can further simplify this, so the denominator will just be left with one value. So if you want, we can further simplify this to rho of L divided by 2 pi epsilon naught, and the final equation comes out to be x minus 6 whole square plus y minus 8 whole square, and then the unit vector will be on top, that is going to be x minus 6 a of x plus y minus 8 a of y volts per meter. So this is the electric field equation when we have the line parallel to the axis, or what we call it as an off axis line charge. So now let us look at some of the numerical problems and see how we can find the line charge distribution of different charges. So we start with the first question, and we want to know how we can solve it. So let's say the first problem at hand is a very basic problem that is going to be applied directly to the given data. So let us say if we have uniform line charges distributed. So let me try to make certain columns out of this. So I have an uniform line charge, uniform line charges distributed along the z-axis. So this is the first hint we get, where the line charge distribution is having a value of 20 nanocoulomb per meter, and we need to find the electric field at 0.68 nz. Okay, so what we do is always in these questions try to visualize it by drawing the axis first. So if I draw the coordinate systems and highlight the points provided, so I have the right hand coordinate system with x, y and z. Now it is not saying that our z axis is parallel or off the axis, so it means that our z axis will be at 0.68 and z is the point where we want to go. So the electric field has to be found at this point, which means if I locate this point, it is going to be somewhere over here. So this is going to be point P, 6, 8 and some value of z, and the line is along the z-axis obviously, so which means that the charges are uniformly distributed on this infinite line. Now we need to know what is going to be the location of the charges or the line. So since it is along the z-axis and the z-axis value over here is z, so we know it is will be 0 for x-axis, 0 for y-axis, and the value of z will be z, because later on in finding it is going to cancel out. So now whenever we are trying to solve these kinds of problems, we say what the first thing is that you have to draw a perpendicular line originating from the source, if the source is one charge, towards the point of interest, and we want to make an angle of 90 degrees from there. Now once we know this, we know that the values of the line charge distribution is rho of L. So just apply the equation to find the electric field, which is going to be rho of L divided by 2 pi epsilon into magnitude of rho and multiplied with the unit vector a of rho. So the value of rho comes out to be, it is going to be the difference of this point with this point, so it is going to be 6a of x minus 8a of y and z equals to 0. Since it's a magnitude, or let's do it one by one so it becomes easy for you. This is rho, and if I take the magnitude of rho, it is going to be the square of the scalar vector 6 square plus 8 square. It comes out to be 10. So finally my answer, I'm going to incorporate everything and give you the final answer, comes out to be rho of L, which is 20 into 10 raised to power minus 9 divided by 2 pi epsilon naught, and the value of this is 10 multiplied by a rho is going to be 6a of x minus 8 of y divided by 10. So we cancel 10 with this, becomes 2, and 2 becomes with this. So the final answer comes out to be, the value comes out to be, let me use this space over here. So electric field finally comes out to be 21.57 a of x plus 28.76 a of y volts per meter. So this is the answer which I am getting, and hopefully your solution will have the same answer. So now let us take another example and see if we want to change the orientation of the line of charge. By changing, I mean it is not lying on the z-axis. Let's say it is lying on y-axis or x-axis for that matter. So let us now take another question. And this time we say that the line charge or line charges of value 5 nanocoulomb per meter is lying on the x and y axis. So now we have two lines. We need to find E. Let's say I want to find E at the point of let's say E at 0, 3 and 4. This is what I want. Okay. So again, we know that the line charge is now lying on the x and y axis, and the point of interest is at 0, 3, 4. Again, we have not been given the off axis line. So which means that when I'm going to draw the axis, so this is my axis, again y, z and x, and now this time my point is somewhere over here. So it is, let's say 0, 3 and 4. Okay, so this is the point what I have. Now I need to draw my lines. So let us say my line or infinite line is along the x and y axis. So this is the x axis. So this is the first line of charges, uniformly distributed. Again, it is like this, and then we have second line with y axis. So this is the second line of charges on the y axis, and both of these lines have the line charge distribution value of 5 nanocoulomb per meter. Same goes for this, it is 5 nanocoulomb per meter. Okay, so what is the first point that we always do when dealing with line charges is we need to draw a line perpendicular to the point of interest. So from any charge, let's say if I want to go, so let us say this is my line originating from the x-axis. It is making a perpendicular angle of 90 degree, and from y-axis again I'm going to draw a line of 90 degree. So both of these lines are meeting at point P. Now let us define the unit vectors for these points. Let us and find the location of these points. So let us say for the x-axis, my point, because I know the test charge is at point 0, 3 and 4, but what is the initial point for, let's say, A, and what is the initial point for point B, representing the x and y axis respectively. So I know that the line is on x-axis, so its value is going to be x, and the remaining points will be at the origin 0, 0. Similarly for y, I know the second point will be y, but the remaining points will be 0 and 0 for x and z axis. So this is the value. Now what is the value of x compared to point P? So since x at point P is 0, so it will be automatically 0. So I can replace this x with 0 by comparing it to the point location of x, y and z. Similarly for B axis, I know that my y is at point 3 and I have to make my y equals to 0. So this value will also become 3. So now once I have these value, I need to find the total electric field at point P. So since I have two lines, my total electric field will be based on the law of superposition principle, which is I'm going to add the first electric field with the second electric field. So let us find the value of the first electric field, and then you can solve for the second electric field, and I'll leave you with the answer of the total electric field. So the first electric field is going to be, let us give it some points for the vectors. Let us say this point is from point A to point P, and this point is from B to P, so I can find my position vectors easily. So E1 is going to be rho of L divided by 2 pi epsilon naught, and this is rho from, let me write the equation. This is rho from A to P, and the unit vector is from A to P. So this means I have to solve for this. Similarly, E2 is going to be rho of L divided by 2 pi epsilon naught, and the rho is now from B to P with the unit vector of B to P, and this is the answer value. So let us solve for one case. I leave the second for you. So rho comes out to be 3a of y minus 4a of z. This is the position vector which I am getting for the one, and the absolute will be, you take the square of this, so rho absolute is going to be 3 square plus 4 square under root, which comes out to be 5. So this means my value for E1 with all the incorporate value will be, I'm going to have a value of 5 into 10 raised to power minus 9 divided by 2 pi epsilon naught, and the value of rho and absolute comes out to be 5 multiplied by 3ay minus 4az divided by 5. So this is what I am getting for the value of E1. Similarly, you can find and solve it for E2. So I'm leaving you with the final electric field, or E total. So this comes out to be 10.8 A of y plus 36.9 A of z volts per meter. So this is the total electric field that you should get. So you need to find the value of for E2 as well as I have did for E1. So this is the solution for this question. Now let us see if we can do another problem that is a logical one, and that is associated with, if I have a finite charge in a circular form. So now let us say if I want to solve another problem, and that is basically, I have a charge filament. So this is what I have, a charge filament forming a circle of radius a, and this radius is basically formed in the xy plane with its center at the origin, with its center at the origin of this circle. Now the details for the line charge are as such. Line charges are as such. So if I have a positive charge when my range is from pi by 2, negative pi by 2 to pi by 2 for the azimuthal angle phi, and it is going to be a negative charge when the range is from pi by 2 to 3 pi by 2. So this is what has been given to me, and obviously if there is azimuthal angle involved, so we know that the coordinate systems might be cylindrical, but this is a 2D plot because we have already been given values in the xy plane. So what we want to do is we need to find the electric field. So for this provided data, find the electric field at the origin. So this is what we want to know. Okay, so let's try to solve this. Okay, so let us first plot this and understand what the data is telling us, and then we can do the analysis. So let us first draw the xy plane, since we have a 2D system. So let us say this is my x-axis, this is my y-axis, this is my negative x, and this is my negative y. And we have to draw a circle, okay, with its center at the origin, and it has a certain radius. Let's call this a in the xy plane, okay. So its radius is similar everywhere, okay. Okay, now what else we know? We need to find the electric field at the origin. So this is what is needed. Okay, so what is the data telling us? Data is telling us that our phi is from 0 between negative pi by 2 and positive pi by 2. So this means if I plot this, I will get semicircles in the positive and negative half. So if this is my x, this is my y-axis, I know that the movement of the axes are such: 0 degree, pi by 2, pi, 3 pi by 2, and this can also be considered as 2 pi. So if I want to first find the value of positive charges, this is between minus pi by 2 to pi by 2. This means that my positive charge is lying in this plane. So this is covering all the positive charges from negative pi by 2 to pi by 2. And for the second point, again, if this is my x and y, I'm covering this side with negative charges. That is from pi by 2 to 3 pi by 2, and this is the origin. So now I have negative rho and positive rho defined visually. So one is covering the right side, which is the positive p rho, and the other is covering the negative side, which is negative rho naught. So this is what I have visually. Now I need to find the electric field arising from these points. So we know that whenever we have a circular formation and we want to find the electric field from a certain point or a certain line, let's say if I want to find the electric field of this line of portion inside the circle, we know its mathematical expression is the differential electric field for that point is going to be dq divided by 4 pi epsilon naught into r square into a of r unit vector. In this case, we know that dq is following a certain radius and a certain angle, so I can replace it with plus minus r a theta, or I can just write it as the radius, which comes out to be a with a certain angle. In this case, the angle is d of phi divided by 4 pi epsilon naught into r. R is basically radius square, which is a square in the unit direction of ar. And what is the value that I'm getting for this line charge? So line charge is basically the value of this small charge on this line. So if these are the distribution of charges, this means that my length is basically r d phi. So this value of charge comes out to be rho phi a d phi. So this is the line charge distribution, and this is the radius that it is covering, which is a d phi in the direction of ar. We can also write this in the direction of a phi as well, but since we are using the same variable for a, this is also fine. Okay, so now what can we do with this? So this is the differential element equation, but we want to find the total electric field on this point. So we know that the total electric field is going to be the integration of this point, which is going to be integration on the right side and the left side of the charge. So I can write it in the form as minus pi by 2 to plus pi by 2. I'm going to integrate what? I'm going to take the value of rho, which is rho naught, the value with a d of phi divided by 4 pi epsilon naught, and this becomes a square. And now what is the unit vector direction? So this is an important thing. How can I write the value of the unit vector? So the unit vector direction is basically going to be the value of if we look at this angle in terms of the radius, so let me try to figure out from here. So if we look at this in terms of the radius, it is forming a certain angle. So I have an angle over here, which means as per trigonometric laws, this can become cos theta and this can become sin theta. So my unit vector is going to have a value of cos of phi along the x-axis plus sine of phi along the ay. If I use my trigonometric identity to have this radius or this portion of this circle. Similarly, my equation then continues to be the second part, which is the integral from pi by 2 to 3 pi by 2, and the value comes out to be negative rho, then the distance a d phi divided by 4 pi epsilon naught into a square. Again, the value of this unit vector comes out to be cos of phi a of x plus sine of phi a of y. So this is the complete equation which I am getting based on the visual data which I have gathered. Now I can see that both the equations are equal, just their signs are in opposite direction. If you can see, this portion of the equation and this portion of the equation are equal, there is only a difference of sign. And we can also see that the ranges covered are almost the same, pi by 2 to negative pi by 2 or pi by 2 to 3 by pi 2. This means that I can write it in a factor of 2. So the electric field which I need to find can be written as minus 2, because both the equations are similar and negative sign is coming because of the direction. Then I can write the value of rho naught divided by the constant 4 pi epsilon naught into a, because I'm not using a square because this a square is going to cancel out with this a and this a square is going to cancel this one. So the common elements or the coefficients have been taken out. The thing that is inside is now the unit vector which I can integrate as per the limits. So the integration can be sine of phi value of minus pi by 2 to pi by 2 minus cos of phi the value of minus pi by 2 to pi by 2, and that's it. So now I just need to solve the integral, which I am hopeful you can do, and then finally from this common factor equation the value I get is minus rho naught divided by pi epsilon naught into a along the ax vector volts per meter. So this is the solution of this problem that is dealing with the line on a circular or a filament forming a circle of radius a. So this is the solution which I have utilized. The important point here was to understand where this value came from. Again, visually we got this, and then we saw that both the equations were same, so we represented it in a form of factor 2, just the sign were opposite, which we have introduced. Again, this is the important factor. I'm hopeful that you will understand this. If not, that you can go back to the point conversion of the rectangular coordinate systems into polar coordinates, and you can further understand how this equation was figured out. If this graphical explanation is not clear, I can give you a hint on that as well. If this point is not clear visually, we can also consider something like this. So if you remember, in the point conversion form, we said that x is equal to a cos of theta and y equals to b sine of theta, or let's take phi because our angle is in phi, right? So now if I want to find the distance vector of this, I can write it as x a of x and then it is plus y a of y. This is the distance vector from this point to this point for this triangle. Now if you input the values, you should get a cos of phi along ax plus a sine of phi along ay. So this is another way to find the value which is shown here in green. Either you can get it visually or you can use the point conversion from rectangular to 2D polar system. So this is how we got this unit vector. So this concludes our lecture on line charge distribution and how we can find the electric field. We did 3 important examples associated with line charge distribution. I'm hoping that the lecture was easy for you to understand. where the important point is to find the equation for the line, and we know that the line charge distribution is dq is equal to rho l into d of l. So this is the line charge distribution, where line charge distribution is equal to the ratio of the charge per unit length, and from here we can find different unit vectors for the given example. That concludes our lecture for today.